ladies and gentlemen. Again, sorry, a bit technical, convenient, but so let me introduce you again, Dr. Béla Gyurcsik from University of Szeged that will have today's lecture at Chemické Horizonty. So he's from the University of Szeged. He graduated. He obtained here their PhD in 1998 and did his habilitation in 2011. He published more than 100 papers, had many conference proceedings and book chapter in English and other 7 book publications in Hungarian. His main research interest focuses on bioinorganic chemistry with the emphasis on the development of artificial metal enzymes and their small molecular models. Small molecular complexes as potential antibacterial and anti-cancer agent. He's also a teacher. His teaching duties are analytical chemistry lectures, seminars, inorganic chemistry applications, bioinorganic chemistry, and biological tools for modern chemistry. He supervised more than 36 diploma works and also 9 PhD students. So I would like to introduce his lecture, Metal Ions Affecting Antibiotic Actions. So.
Okay, thank you, Rastio. And thank you very much for this opportunity to come to Bratislava and have the lecture within this nice series. So, ladies and gentlemen, today my talk will be about 2 enzymes which are related to antibiotic action of bacteria for their survival. And in fact, I come from University of Szeged from a bioinorganic chemistry research group. And as such, we are interested in studying the interactions between metal ions and biomolecules, as well as their models, as well as some drug-like molecules. As you can see here, this is a poster of our research group, including different studies. So this time, let me first apologize for those people who listen to my lecture at Smolenice, because there will be some overlap on it. I try to add new information as well. But okay, I will start with the first enzyme, which is TEM1 beta lactamase. In fact, it is a group of enzyme, and we were synthesizing only one of them. And you can see here the structure, crystal structure of the protein, which contains several potential metal binding sites. Like on the surface, there are histidine pairs, 3 of them, and there are methionines for soft metal ion binding. There is a disulfide bridge which rarely binds metal ions, so it's not really a good binding site. And in spite of this enzyme is not a metal enzyme. So it hydrolyzes the beta-lactam ring of beta-lactam antibiotics using a serine side chain. It's a serine 70, which serves as a nucleophile in attacking the beta-lactam ring. Okay, so we had the aims to synthesize, purify the protein, characterize the protein. Then we wanted to see what is the effect of the metal ions on the protein's structure, on the protein's catalytic activity. Do the metal ions, non-endogenous metal ions, affect the catalytic activity of this enzyme, which is very important. So, because of the metal binding sites on the surface, histidines, we choose as a purification strategy IMAC, which is immobilized metal ion affinity chromatography. And this affinity chromatography is usually used for those proteins which are artificially histidine tagged. So it means artificially a hexahistidine string or decahistidine ring is just fused to the protein in order to bind it to the immobilized nickel ion on the resin. And then based on this property, the protein can be selectively purified. It is not usual to use this affinity chromatography for native proteins. And in these two polyacrylamide gel electrophoresis picture, you can see that after the first immobilized metal ion affinity chromatography step, we have enrichment of our protein, of the band of our protein, but still there are many other proteins in the mixture. But in the next second optimized step, we could get almost pure protein. So we only polish this one finally in order to get a pure protein. It was interesting to check the mass spec of the protein because we have identified the protein being different than it was proposed or it was announced by the producer. So there was one amino acid exchange in that, but I should say that it is almost natural because bacteria evolved many mutant variants of this beta-lactamase enzyme in order to be resistant against new antibiotics. At least we know the precise structure and precise molecular mass, and based on this one, also the concentration, we could evaluate the CD circular dichroism spectra for the secondary structure elements or fraction of the secondary structure elements in the protein. And you can see that by means of different programs which we used, CDS, STR, and BestCell, these are available on the internet freely. We could get similar secondary structure element composition then calculated from the crystal structure itself. This crystal structure is not exactly for the same TEM1 beta-lactamase as we studied, but there are two amino acids differences. However, if you compare the different crystal structures of different TEM1 beta-lactamases, you can see that they are very similar. So we can say that probably this protein is functionally active, is in functionally active form. Okay, so we started to investigate the catalytic activity of this protein, and we choose ampicillin as a beta-lactam antibiotics, which is not the best substrate of it, since it doesn't have any absorbance in the visible range or no color change during the hydrolysis. However, ampicillin is commonly used in our laboratories for selecting the bacteria in the liquid broth. So therefore, we stayed with ampicillin because we wanted to see the effect of the beta-lactamase on ampicillin. And we carried out spectrophotometric measurements as a function of time following the absorbance during the hydrolytic procedure in different systems. So we constructed systems with different substrate concentration, with different enzyme concentration. You can see the enzyme concentrations are extremely low in nanomolar range, 10 to minus 9. And this was the first difficulty which we faced, that at the beginning it was very difficult to reproduce the experiments. We used very tiny volumes, few microliters of the protein, and in addition we needed to dilute it a lot. And during these procedures, some of the enzyme has been lost, adsorbed on the surfaces, and so on. So we really needed to repeat the experiments in parallel experiments with the same batches at the same time in parallel. with different composition, and then we decided that we will fit the whole progress curve of the catalysis instead of doing the evaluation by the traditional like Michaelis-Menten formalism. And in addition, if you see, the first part of the curve is very steep, so it means that the first step of the reaction is very fast, and afterwards we would expect that the absorbance becomes constant in time. However, at the extended time period, we could see a continuous decrease, a slow decrease of the absorbance, and by this suggests that something happens with the product. So there is an initial catalyzed hydrolysis of ampicillin, and then the product 1 of the hydrolysis is probably turned into product 2. And in fact, if I come back just for a moment, you can see here that the dotted line is the fit of the catalytic curve if we neglect this second product. And the symbols are the experimental results, data. And then there is another line, which is exactly nicely fitting also the last part of the curve. In this case, we included the product 2 in the evaluation. So we just wrote the model of our experiment. Then we wrote the differential equations, which has been solved by the ChemMac program, which is developed by Pentler Gabor in our university. And then we could get the parameters, the catalytic parameters, especially the rate constants. You can here see, probably you cannot see, but at least the K3, which is the traditional K-cut value, is in the range of the literature values, which we can get. It is 344. However, if you look at K4, which is related to the conversion of product 1 to product 2, it is a very, very slow process, 10 to minus 5. However, you could see that we have 390 micromolar of the substrate and 0.something nanomolar of the enzyme. So since we have a high concentration of the P1, in fact, the substrate, which is converted to P1. Therefore, the rate of the conversion is significant here, and therefore we can see it in the catalytic process. We could also identify what happens in the reaction mixture, and after like elongated time, we measured the mass spec of the mixture, reaction mixture, and we could see the product 1, which is already relatively low intensity compared to the product 2, which was continuously increasing. And this product 2 has 44 Daltons or atomic units less than the first product, which means that probably this ampicilloic acid has been decarboxylated non-catalytically to amyloic acid. So, but that means that we should take these things into account when evaluating the catalytic curves, because if you would do that by traditional Michaelis-Menten formalism, and let's say you can make this Lineweaver-Burke evaluation, you can see very nicely that the Michaelis-Menten constant depends a lot on the choice of the A infinite absorbance. And this is because the absorbance is continuously decreasing. So the choice of the A infinite is ambiguous. And that gives you a big ambiguity in the Michaelis-Menten constant. And also, of course, the K-cut as well. Okay, so at least we learned something about the enzyme substrate system. And now we wanted to see what happens if we add some toxic non-endogenous metal ions to this system. And increasing the amount, for example, of mercury, which is a very soft metal ion, you could see that the catalytic activity decreases continuously. Yes. So on the other hand, if we add 10 equivalents of not only mercury, I mean, in one experiment, mercury, but also in another one, cadmium, and in another one, nickel, surprisingly, we could see, you see the red one is the catalytic curve of the enzyme substrate system. Black one is for the mercury. It has less activity. However, cadmium and nickel seems to activate the enzyme because we have higher activity. It's not very big change, but still we can see this and we could reproduce these changes very nicely. So that means that probably the metal ions interact with the protein and they influence the catalytic activity. And we already know that the three his pairs probably can bind quite strongly nickel. This is proved already by the purification, but probably more weakly cadmium and even weakly mercury. And we have methionines, which are soft, which have soft donor groups like the thioethers, and they can probably more strongly bind mercury than cadmium and nickel. And we have checked, this is the network of the 9 methionines, and the red one is the active center serine. So you can see that there is a nice network of methionines around the active center. Even if you look at the left side, you can see the 8 angstroms sphere of the serine residue. This is the serine residue here. And within 8 angstroms, you have 3 methionines, which may bind mercury. And if we suppose, we hypothesize that if mercury binds to these places, probably it inhibits the enzyme because it is close to the active center. So it may just irreversibly block the active center. And indeed, when we evaluated the curves with mercury, in the presence of mercury, we could obtain exactly the same catalytic parameters as without mercury. So as for the free enzyme, just by decreasing the enzyme concentration. So that means that part of the enzyme became inactive. So in fact, the functional enzyme concentration decreased. Of course, that means that Vmax is decreasing, but we did not calculate that one because we did not go for the Michaelis-Menten formalism. Okay, we wanted to know what happens when mercury binds to the enzyme. And in fact, it was not really promising. We tried several spectroscopic methods like circular dichroism spectroscopy, mass spectrometry, and even a very exotic perturbed angular correlation of gamma rays spectroscopy, which was carried out by our collaborators in Denmark. And none of these experiments, as you can see, for example, for CD spectroscopy, showed a very small change, small but continuous change. Then also, when we wanted to see the mercury adduct in mass spec, we had problems. We could mainly see the free enzyme with some sodium or potassium adducts, and we could see only tiny amount of mercury. So all these results showed us that mercury does not bind strongly to the enzyme, but it can bind weakly to the methionine sites, and even we cannot say whether one methionine site or 2 methionine sites are occupied at the same time, partially. Okay, only partially. So that was with mercury. What happens with nickel? Nickel activates the enzyme, do not forget that. What we know is that already from the purification experiment, we know that it can bind to the surface histidines probably. We also carried out circular dichroism spectrometric experiments, but since the binding is at the surface, at already preformed sites, there was no significant change in the CD. So it was not informative. for that. And finally, we carried out mass spectrometric measurements. And in mass spectrometric measurements, we could see that already at 2 equivalents of nickel, we have as a major particle, a nickel protein product. And when we increased the amount of nickel, we still got the nickel protein, nickel 1 protein product as a major product, which means that probably the second and third nickel, especially the third nickel, binds very, very weakly. But at least there is a binding of nickel to the enzyme, and that may increase the local nickel concentration around the enzyme. And this nickel, which is close to the enzyme, may bind also to the ampicillin. And then probably it can activate the ampicillin. This is our hypothesis right now about the possible outcome of the experiment. So just one more thing which I missed to tell, but probably you recognized already. So we had a very, very large excess of the substrate compared to the enzyme. And we had the metal ion to enzyme ratio maximum up to 10. So it means that also from metal ions, we had very, very tiny amount in this system, which is very important. And it is important because we had a different situation when we tried to check the effect of the metal ions on the bacterial growth. And we used minimal media for the bacterial growth. Minimal media means that we only add those components to the broth which are necessary for the bacterial growth, so that we can control. In fact, we add only chemical substances, which we know precisely how much did we add to it. And then we can control the system very nicely. And we used bacteria which can express the enzyme, 10-1 beta lactamase enzyme. Although I should say that we don't know exactly what is the enzyme concentration in this system, because the bacteria will produce some certain amount of the enzyme. Okay, so we wanted to see what happens with the bacteria if we add different amounts of metal ions. And you can see the empty symbols. The empty symbols are related to metal ion containing systems without ampicillin. Whenever we added also ampicillin, then we have the full symbols. Okay, so what happened? At this condition, what we used here, you can see that cadmium, which is the yellow, it has the yellow symbols, with or without ampicillin was not really toxic for the bacteria, because this is the curve characteristic for the normal growth. Okay. However, when we added nickel, we have in 1 micromolar and 10 micromolar. You could see 1 micromolar is still normal growth, but 10 micromolar became toxic. And with mercury, even with mercury is this one, it's 10 micromolar and 1 micromolar, these two, even at 1 micromolar concentration, were very toxic. So the bacteria died. What happened when we add ampicillin to this system? When we add ampicillin, the toxicity of the metal ion diminished. We don't have the toxicity anymore in the presence of ampicillin. So what we can say now we have high concentration of the metal ion, much higher than the enzyme supposed. And then this metal ion, which is toxic, can bind to the ampicillin. It binds to the ampicillin and it forms an adduct, which is not toxic anymore for bacteria, which is a little bit unexpected. We would expect that ampicillin should be toxic for bacteria, especially if they don't have 10 beta lactamase. Metal ions should be toxic. So it's a little bit surprise for us. And in fact, we tried the same experiment, which is not shown here, with another antibiotics called kanamycin. And in that case, we use different bacteria which are resistant to kanamycin. And in that case, the addition of the antibiotic, kanamycin antibiotic, did not cancel or compensate for the toxicity of the metal ions. So because it cannot bind metal ions. So this is probably a kind of proof for our hypothesis. And then just here are summarized the suggested effects of the metal ions on this system. And we say that there is a double selection of the system because metal ions can bind also to the enzyme, which causes changes in the system, and metal ions can bind also to the ampicillin system. And the different types of metal ions like mercury and nickel cause different effects. So there is a double selection against this one. And these are the conclusions for the first topic. Okay, the second topic will be about another bacterial toxin. It's this toxin is produced by bacteria in order to protect themselves from another bacteria, and usually it is expressed in stress conditions. However, I will try to relate this enzyme, which I will talk about. It will be so-called N-chole7, you will see very soon. I will try to relate it to artificial nucleases. Why? So artificial nucleases are very nice agents. They can, for example, designed to cleave a DNA molecule which has an aromatase nucleotide in. So, for example, in inherited diseases or something like that. And then if you cleave the DNA close to this aromatase site, then by homologous recombination, if you have a homologous sequence in the cell, the DNA can be repaired and the native DNA sequence will appear. And by means of this, even these inherited diseases could have been cured. So it is not so easy because we cannot do that right now. And one reason is that we cannot do is that we don't have the proper enzyme for it. You see here different enzymes, different artificial nucleases, which consists of nuclease domains, but all these nuclease domains, nuclease parts of the enzymes, cleave the DNA non-specific. So you can imagine if you have these swords and they come alive, and they will cut everything and everybody here. So this is not very good. It's much better if you have a samurai, yes, and the samurai will direct the swords. So it will only cut the target, nothing else. What is the samurai? Here we have the samurais as proteins or oligonucleotides, for example, zinc fingers or other homing proteins, or we may have also CRISPR-Cas9 system, which you probably heard about it, in which you also have an oligonucleotide as a samurai directing the swords. And for description of this system, a Nobel Prize has been awarded to these two nice ladies in 2020. However, still we cannot use these enzymes for gene therapy in vivo. So they are carrying out experiments in test tubes, and then they try to use the corrected DNA or corrected cells as a cure. However, in vivo, the problem is that still all these type of artificial nucleases have off-target effects, so they can cleave also off-target. So the aim was to try to develop an artificial nuclease which has a safe control mechanism. So that means that it stops cleaving the DNA if in case of any damage of the enzyme in the cell. How much time do I have? Okay, perfect. Thank you very much. So we have chosen N-chole7 as a model system for our newly developed artificial nuclease. And the reason of that is multiple. One is that it is a metal enzyme, and we are bioinorganic chemists, so we like metal ions. So we have metal ion in the active center, and this active center is at the C terminus of the enzyme. And then there is an arginine at the opposite end of the protein in the chain. However, in the structure, they come close together, and they, in common, cleave the DNA. If you remove the N-terminal part, the C-terminal part will not really work. And that's a very nice opportunity for regulation of the enzyme, because both ends are necessary. So if you damage this enzyme at any part of the enzyme, it will stop working. The problem is that this enzyme is a non-specific DNA cleaving enzyme, so we need to convert it to specific one. But first, let's learn something about this NCOLE7. So the NCOLE7 has then the interaction between N and C termini. So by means of this, we can fine-tune the nuclease activity. We can also fine-tune the structure, the catalytic activity by changing the structure, and we will see that it has a pre-organized metal binding site. Here, I show a crystal structure of a mutant NCOLE7 protein, and the mutation was that we deleted the N-terminal part, which contains the arginine, which is necessary for the catalytic activity. And then we deleted that one. It's called the catalytic activity. So that means that the activation by the N-terminal part is necessary for the action. We could prove that very much. Then we also synthesized different mutants of the enzyme. I showed this N-terminal part consists here, which is deleted, consists of 4 amino acids. K is lysine, R is the arginine, then N is asparagine, and K is again lysine. So you see there are quite many positive charges here, and arginine is special among them. But we also made a mutant in which we just exchanged arginine to glycine, and then crystallized that one together with DNA molecule. And you could see very nicely that if we overlay the structure, our structure, where we have lysine, and the native structure where we have arginine, you can see that the lysine can partially overtake probably the function of arginine, because in the absence of arginine, lysine directs to the substrate. Of course, we know that this enzyme is much less active. It has approximately 10% activity of the native enzyme. And probably the reason is that we have different mechanism in this case. You can see here there is a histidine side chain which is not binding zinc. There are 3 histidines binding zinc. There is a 4th one which activates water molecule, which will then attack the phosphodiester bond to cleave it. However, then the proton from histidine, which comes from water, will be transferred to this alcoholic OH as a and then we hypothesize that probably arginine has a role in this proton transfer, and this proton transfer exists in this way. Then we carried out several other mutations, and you can see the more positive charge. The more positive charge we have deleted from the enzyme, from the N-terminus, the less was the activity. This is the native enzyme. It's very quickly degrades the DNA. This is the KGNK, which has 10% activity, and the others has much less. This was an interesting experiment. We did so-called linear dichroism experiment. And in this linear dichroism experiment, we had a rotating cell in a kind of thin layer. And in this rotating cell, the large molecules like the genomic DNA, this is a calf thymus DNA, which we investigated here, can be ordered and provides linear dichroism. However, when we cleave this DNA by the enzyme, the DNA molecule becomes shorter and shorter, and then this linear dichroism is just disappearing, and you can see here it comes to zero. It was a nice experiment. Okay, so the next one, after fine-tuning, we showed that there is an amino acid in the sequence. This is the sequence of the enzyme. Here we have the positively charged N-terminus. Here we have the histidines which bind zinc at the C-terminus. And there is this tryptophan here, close to the N-terminus. And if we deleted this tryptophan, with the new proteins, new purified proteins, we could get completely different CD spectrum. This was the native enzyme CD spectrum, and for those mutants which did not contain this W mutation, and these spectra were for those enzymes in which we deleted, or not deleted, but mutated this to glycine or alanine. And that means that while the native enzyme has a nice alpha helical rich structure, this is characteristic in CD for alpha helices, in opposite to that one, the W mutants have CD spectrum characteristic for random or unordered structures. So the W is very important from the point of view of the structure. On the other hand, you can see here that not only for the structure, but for the metal ion binding as well. Maybe you can see here. This is the protein, the KD related to the zinc protein complex. And you can see that the native enzyme binds the zinc ion with nanomolar KD value, so it's quite high stability, while the W mutants decreased the zinc binding ability by 3 orders of magnitude. So from nanomolar, the KD became micromolar. On the other hand, if we add, for example, immunity protein, which is an interacting protein with NCOL-E7, it inhibits its action in nature, or DNA or zinc, especially large excess of the zinc, then we could get a very similar spectrum than for the native one. This is the example when we had the W immunity protein complex minus the immunity protein CD compared to the native NCOL-E7. So it means that the differential spectrum is exactly the same as the native one. So immunity protein induced the native structure of the protein. And then you can also see that in this case, I think if I go further, you can see that in this case, if we add immunity protein to the protein and zinc, then the KD again became nanomolar. So not only the structure, but also the zinc binding site is very important. Okay, so that means that, in fact, that means that the zinc binding site should be a kind of pre-formed zinc binding site, specialized for zinc. And we can also see here, for example, if we add, these are CD spectra. For example, this is the CD spectrum of the enzyme, and there is a slight shift of like 2 nanometers and slight change in the shape of the spectrum upon adding zinc. So there is not a big change in the structure, just a very small change in the structure, which also suggests that it is preformed. We have this shift. And then, okay, now we started to add different types of metal ions to the enzyme. And we can see with copper, with cadmium, with nickel, we have the same change in the spectrum. Same change as with nickel. So that means that that the enzyme can bind also these other metal ions as well, and probably in the same manner, at least in very similar manner than zinc. And I think it is not here. Yes, it is not here. But in my previous life, when I was a bioinorganic chemist dealing with model compounds, I studied the metal complexes of small peptide molecules, like hexapeptide having 3 histidines. And if this peptide was bound with 3 histidines to copper and with zinc and to zinc, we measured the stability constants. The ratio was exactly the opposite. So we had nanomolar Kd for copper and micromolar Kd for zinc. So that also shows that it is a special arrangement because it binds zinc more strongly. Is it true? Yes. In fact, we try to measure the mass spectra of the APO enzyme. So it means we removed all the metal ions from the solution and then added different metal ions like zinc, cadmium, copper, and it is not very nicely seen here, and nickel. And in mass spec, we always could detect the appropriate metal bound enzyme. So it can bind. What happens if we do the same? Okay, this is the copper. With copper, it was a little bit difficult to prove that this peak belongs to the copper-bound enzyme. So therefore, we simulated the isotopic distribution of the mass spec peak. And you can see here the gray is the simulation for zinc. The blue is the simulation for copper. And then the blue overlaps with the black, which was the experimental spectrum. So it means it proves that it is indeed a copper-bound enzyme. However, if we carried out the same experiments with different metal ions in the presence of zinc, one equivalent of zinc, then in all mass spec, we got the zinc-bound enzyme. So none of the other metal ions were able to bind the enzyme in the presence of zinc. Zinc binds more strongly. Okay, what happens with the catalytic activity? And this is again a very interesting question because we were surprised to see that the KGNK enzyme, this is the APO enzyme, without any metal ions, cleaves the DNA. How we can see that? This here you can see that we use plasmid DNA, and the plasmid DNA exists in 3 different forms. This is the superhelical, which is the intact form down. Then this is the open circular, which runs more slowly, much more slowly. And then if there is further cleavage, you can get linear DNA, which is somewhere in between them. And if you have many subsequent cleavages of the linear DNA, the DNA becomes smaller and smaller. So that means that you will get a smear down, down, down. The smaller is the DNA, the faster is running in the gel. Okay? So you can see that the APO enzyme without any metal ion was active. And that was a surprise because in the literature, it is written that it is a zinc enzyme. And when we purified the enzyme, it was also zinc-bound form from the cells. So certainly our experiment says that it is a zinc enzyme. However, when we add zinc to it, it becomes much less active than the APO enzyme. Certainly, we should say that this is a zinc enzyme, but surprisingly, the APO enzyme is more active than the zinc-bound form. Of course, in the nature, there is zinc-bound form of it. But in test tube, we can study the DNA cleavage with the APO enzyme as well. Okay, we could see that the same situation occurs with copper. If we add copper, we again get less active enzyme, probably similarly active than the zinc. It's slow activity. When we add cadmium, we get higher activity than zinc and copper bound enzyme, but less than the APO enzyme. And even if we increase the cadmium, the activity is decreased. And this is probably because still we have some free enzyme here. We could also see from the mass spec, if you go back to the mass spec here, you can see that in the presence of cadmium, this is the presence of cadmium, we could not fully, even we have some of the APO enzyme. So that means that cadmium binds to the enzyme weakly, and still there is some APO enzyme which is more active. And then when we add nickel, we were again surprised because with nickel, we had extremely high activity. So that suggests us that the enzyme can bind nickel as well. And probably with nickel, it is much more active. However, that means that if we have non-endogenous metal ions available, probably we can get much more toxic or aggressive bacteria in the environment, let's say. Okay, then I learned that we don't have too much time, so I will just show you one more. The last thing is the design of the artificial metal enzymes based on NCOL-E7. So what we did, we replaced the non-specific binding DNA binding site of the enzyme with the zinc finger, which recognizes the DNA specifically. And to the two termini of the zinc finger, we bound the N-terminal regulatory part and C-terminal catalytic unit of NCOL-E7. And we found that there are pairs, at least there is one pair of the short and long enzyme containing both the C and N-terminal and just the C-terminal part, in which we have the full enzyme active and the shortened enzyme inactive. So that means that the regulatory part works. And we also could see from the DNA study from the cell that this toxicity is due to the hydrolytic activity, cleavage of the DNA. And then finally, this is my final experimental slide. Hopefully, we could show very nicely in a test tube experiments having enough 150 millimolar sodium chloride in the solution that the superhelical DNA, which did not contain the recognition site of the zinc finger, was not cleaved even after 72 hours. But the one which contained one site, it was converted from the superhelical form to the open circular form. So this shows that non-specific DNA is not cleaved, specific DNA is cleaved. And also we could check that when the regulatory part of the enzyme is missing, none of the DNA, neither non-specific nor the specific, was cleaved. So we have the regulation and we have the specificity, and we would like to continue on this way. Okay, then I will not read the conclusions. Now I would like to thank my co-workers, mostly students and PhD students who worked on this topic, and Zayat Nafai, who worked on the TEM1 beta-lactamase topic, and then also for the grants which provided financial support for us. And I would like to thank you for your attention.
So thank you very much for your lecture, Béla, and we are open to the discussion. Okay.
First, I must appreciate the very logical structure of your lecture. I put several questions on paper when you have your lecture, but in the next part, this question was answered. That means nothing. But I have still one question. Why do you choose mercury, cadmium, and nickel as metals for your study? Why not calcium or magnesium or ferrum, iron?
Yes, that is a very good question. Thank you very much. In fact, the reason for nickel was very evident because of the nickel affinity chromatography. So previously, as I told previously, we studied many metal ions, many peptide ligands containing histidine amino acids. And we know that histidine can bind nicely to probably zinc, copper, nickel, cobalt, and so on, not iron 3. and not calcium and magnesium. So, but the main reason for nickel was the nickel affinity chromatography, because sometimes I didn't tell you that there is another group studying NCOLI7 enzyme. No, NCOLI9, sorry, NCOLI9 enzyme, which is very similar to ours. And that group claims that the native metal ion in that enzyme is nickel. And we suspect that that might arise from the nickel affinity chromatography purification, some remaining nickel, which is extremely active anyway. Even if there is small amount of impurity, it is extremely active. Mercury was chosen because it is a soft metal ion, and we knew that there are quite many soft donor groups. So we wanted to have something which can bind to methionines as well. And cadmium is somewhere in between them. All of them are toxic.
Can you show us once more, please, your CD spectra?
Which one?
CD spectra.
Yeah,
Any.
Okay.
These couples. For example, this one.
This one?
Yeah.
Yeah.
No. Also this one. All right. The difference in the spectra is very small.
Yes.
It is statistically evaluated that this is a really difference, or it is a statistical deviation.
Yes. In fact, we have repeated this spectrum extremely many times. If there was an error in the intensity of the spectra, then the repetition, all these repetitions will decrease the random error in that one. However, the change, not this one, maybe the other one. Yeah, these. The change in the wavelengths is much more how to say certain, because we calibrate the wavelengths extremely precisely and it does not change. So if you have that change, that means that there is an interaction. And also what we could do, and I think it is, I'm not sure where it is, but probably here, just the colors are not very nicely seen. Here we have the Kg and K only, which is here. Then we have the zinc 1-to-1 and 1-to-3, which are here, which means that 1-to-1 is already enough to saturate the enzyme. But when we add EDT in equal amount, then the spectrum comes back to the APO enzyme. So also we can make it reversible.
Real difference.
Yes, it's a real difference. Maybe that was the short answer.
Next question, Docent Schwartz.
Béla, thank you for a nice and logical lecture. So my first question actually was why you have chosen just this type of molecule of metal ions. Is there any reason for that, not to use more abundant metal ions like iron or copper ions, which are in the living system most abundant? But you have a question, you have answered this question. So second one is dealing with the NCOLI7 enzymes. Did you study the mechanism? If you observe the nuclease activity, APO enzyme as well as zinc containing enzyme, what was the mechanism of this nuclease activity?
No, unfortunately, we didn't study the mechanism, but we have suggestions. I'm not sure that they are here. We have suggestions. The suggestion is that when we do not have the metal ion in, we have at least 4 histidines which can participate in a proton transfer reaction very easily. So that might be probably the reason of the high activity of the enzyme, because every metal ion cancels, or at least not nickel, because nickel is different. And in the case of nickel, since we have a tetrahedral binding sites specialized for zinc, and nickel would usually be octahedral. So there should be a few water molecules around the metal ion. And usually, this is different with NCOLI7, but usually with metal hydrolases, the metal ion bound water is polarized and then it's deprotonated. So the OH group will behave as a very, very efficient nucleophile. And probably this is much more efficient process than the deprotonation by the histidine side chain, water deprotonation by the histidine side chain. And probably that is the reason that nickel is much more active. In fact, the other group which I mentioned, working with N-choline, they published the crystal structure of nickel-bound protein, and indeed there was a water molecule bound to nickel directly.
And in your NCOE7 enzyme, what is the chromophore or coordination number around the zinc ion?
There are three histidine side chains which are bound to zinc, and in fact we know that from crystal structure.
So it's 3 coordinates?
It's in fact it is 4 coordinated with water. There is one water molecule. However, when the substrate is bound, the DNA in fact replaces water. So there is no water during the catalytic reaction around zinc.
Yeah. Okay. Thank you.
I'd like to ask if there is any questions from the internet audience.
Well, in this point, I would like to encourage the audience in the Microsoft Teams meeting to ask the questions. And in the meantime, maybe I have one more simple question. Why actually did you use the CD spectra? Why not simple UV spectra? UV spectra wouldn't see you such interactions with metal ions?
With zinc, you certainly cannot see because it is colorless. In UV spectra, it may happen that you can see some charge transfer bands, but nothing about the change of the structure of the protein. And in fact, I am afraid that the sensitivity of the UV visible spectrometry is much less than the CD. So in CD, we measured in few micromolar solutions, which is probably not enough for the UV visible spectroscopy.
Okay, okay. So in this way, you cannot use also NMR also?
Pardon, in this way?
In this way, you cannot use NMR as well?
Yes, I would say that we already measured some NMR. It is not yet published. The way to do that is to synthesize a protein which is enriched in carbon-13 and nitrogen-15. And that we also do in very simple way. It looks difficult, but the very simple way is to grow the bacteria which express the protein in carbon-13 enriched glucose, in the presence of carbon-13 enriched glucose and nitrogen-15 enriched ammonium chloride in minimal medium. So it's possible, just it is extremely expensive.
Yeah, of course. Yeah. Thank you very much.
Welcome.
And I would like to ask you also that you showed that the enzyme cleaves DNA also specifically, but if you can change or mutate the enzyme, that will it be possible to cut the DNA at a special place?
That means specifically, yes. So in fact, what we did here is that we introduced the zinc finger protein. It can be replaced by any other specifically bindings. Zinc finger proteins have the property that they can specifically interact in the major groove of the DNA with the nucleotide, specific nucleotide sequence, and they can be designed or redesigned to many different sequences. So in fact, because this is a traditional small protein which can recognize specifically DNA, we choose zinc fingers. And then in cells, we could not observe specific DNA cleavage because the plasmid DNA has been completely cleaved. And we suspect that this is because the plasmid DNA exists in non-protected form. So there is no any protein which can compete with zinc fingers. However, if you have DNA binding, but yeah, but this is not our project anyway. So zinc finger nucleases exist and they are studied very well. However, in test tube, we could very nicely see the difference of the cleavage between the DNA which does not contain any sequence which can be recognized by our zinc finger, which is included here. And there was another DNA molecule, which this is a plasmid DNA, which contained only one of these cleavage site. And if you cleave only one side, it means single strand cleavage. So it means in single strand cleavage, the superhelical forms goes to open circular and not more. That's very important. No linear DNA appeared and no fragmentation of the DNA. So it was really specific, but it is due to the zinc finger protein.
Okay, thank you very much. And so is there any other questions from the MS team audience or here?
Apparently not.
So I would like to thank you very much for your lecture, Béla, and also the audience. So thank you very much.
Thank you very much,
Thank you very
Laszlo. And thank you.
Whoosh.